It's good? Yes. Okay, thank you. So let's start from, so here is what I want to do with you today. And I think that since we have a lot of pictures to look at, we'll probably just stay with the slides today, and I will add comments on the blackboard when is needed. So first of all, we go back to where we left yesterday. And we'll start looking, so I wanted to elaborate more and show you where the full structure of the quantum theory of the Standard Model comes into play in Higgs physics. And therefore, we will look at that starting from where we left yesterday, which is the calculation of branching ratios, and that's a very simple first example. And then we will go to look at electroweak precision fits, from which we also get a lot of information sorry, about the Higgs sector of the model. Then we will then question if we do have from the structure of the theory other constraints that can be useful for us to consider. And that will be the place where we see very clearly how the study of the Higgs, as a Standard Model Higgs, is very much related to new physics. And it tells us, it's a sort of trait d'union between what the Standard Model is as an effective theory and whatever is its ultraviolet completion. And studying just the property of this single degree of freedom will tell us a lot about that. And so we will just look at few options beyond the Standard Model, just briefly, just to see that there are, and to see that they may even do better than the Standard Model itself, and to see that they are precisely where the Higgs of the Standard Models, if it exists or not, tells us they are. They should be, at least. And then, well, we can, at that point, we should be convinced that still we cannot say anything without data, just from the trivial point of view of just saying seeing or not seeing what we have been discussing, but also from the point of view of what many other new degrees of freedom that could be there and could help us. And we move on to the next lesson that will be tomorrow, just considering colliders and which kind of physics we want to discuss at colliders. So first of all, as a first point there, you may say, well, why don't we just go directly to quantum effects? I just wanted to make sure that we made this point yesterday. So yesterday, the last transparencies that we saw, and the only transparencies that we saw during our lecture was this one about branching ratios and width of the Standard Model Higgs bosons. And I just had invited you to think about the shape of the different curves that we have here, where they happen, in which mass region, and to see if you could somehow reproduce some of them and get the numbers that you get out of black boxes like HDK or others. This plot is from the LHC Higgs cross-section workshop that happened last year and is still ongoing, and is therefore very updated with the last tools and the last kind of corrections that are available, and so on and so forth. Now, the point that I wanted to make sure is just that we are able to do this because the only really parameter the whole picture depends on is the mass of the Higgs. Right? And then you might be there wondering, well, the mass of the Higgs that we had on the blackboard yesterday is related to lambda and v, right? So the mass of the Higgs is 2 lambda v squared, where lambda is the quartic coupling and v is the vacuum expectation value of the scalar field of the Standard Model. Now, you would think that you need at least 2 of them in order to describe the whole physics of the Standard Model. Well, we picture everything in terms of m Higgs here as if it was the only unknown, and it is, as a matter of fact, because out of 3 you need 2, but 1 is measured. So the V, actually, that we use, 246 GeV, that we normally use, is measured in mu and decay. And the reason why it happens, and probably this is clear to all of you, but the reason why it happens is just mu and decay is a low energy process. So you can just use, this is the process that you are looking for, right? And this is a W, right? But in the low energy limit, so for Q squared much smaller than MW squared, which is the proper energies for a process like this to happen, this is a 4 Fermi interaction. So the decay of this object, the decay rate for the muon decay is just go like G Fermi. So it would be something that is proportional to G squared electroweak and MW squared. And MW squared, we said yesterday, is expressed in terms of G and V, right? So MW squared, the Standard Model, is a half GV. So this is a fourth G squared V squared. And so you see that this goes to 1 over 2 v squared. So you see that v is square root of 2 gf to the 1/2. So if you measure gf that you measure in muon decay, you measure v, right? And gf has no error, basically. So it's that number, 1.6639, something like that, 10 to the minus 5 GeV to the minus 2, where you see the GeV to the minus 2 over here, right? So this is where V is coming from. The 246 is precisely coming from there, right? And therefore, M Higgs in the standard model is really the only parameter that you have, right? And that's why it's so powerful to do an analysis in the standard model, and why it's not better, but it's much more instructive than not taking any model in which you have a lot of other parameters to play with, right? So this is the origin of, this is the first comment that I wanted to make, because I wasn't sure we really emphasized this enough or at all yesterday. So what goes into this plot? Clearly by now you have discussed about it, you already knew, you thought about it, and there are a lot of corrections due to the quantum theory, to the quantum structure of the theory that you have, so due to the quantum structure of the standard model. So the standard model is made of the electroweak sector, and is made of the strong sector of QCD, and both strong and electroweak interactions are important and play a really important role. And I'll look at that with you with a few examples. So the first example that we want to look at, two examples that we want to look at, and one in particular, is the decay of the Higgs into fermionic degrees of freedom, so leptons and quarks, and the decay of the Higgs into vector bosons, so electroweak gauge bosons. So if you do the simple exercise of calculating it at 3 levels, these are the two expressions that you get, and you have features that you expect, like for instance the fact that is, in the case of fermions, is proportional to the mass of the fermion square. There is a phase factor. This beta is the usual 1 minus 4 of the mass of the decay products divided the mass of the decaying particles squared. And the delta that are used here are just numbers that they are differ by degrees of freedom between the W and the Z, and NC is just a color factor, so it's 1 for leptons and it's 3 for quarks. So after this, if you use these formulas and you just plot a curve as a function of M Higgs, of course you get different results from what was on the previous plot. And let's see, for instance, in what goes into the prediction of the decay of a Higgs into fermions. In particular, let's see what goes into the prediction of the decay of the Higgs into quarks. So if you now switch on the full structure of the standard model and you take into account QCD, you would have, of course, to take into account QCD corrections, so gluon and quark corrections, so virtual correction and real correction to this process. So it's still the decay of a Higgs into 2 quarks, but inclusively you would have also quarks emitted and gluons emitted in the final state that then are defined and lumped together with the products that you have in the final state that are quarks, so are strongly interacting particles, they radiate. So if you do the calculation at a given order in QCD, you will in general be able to write, well, you'll always be able to write your expression as something that looks very much like what you started from, so the 3-level expression, times 2 terms that are corrections. And these 2 terms are a piece that both come from both a QCD piece and a piece that depends on the mass of the top that has still a QCD origin. On top of this, you will have to turn on electroweak correction and therefore calculate also electroweak correction that I do not write in these formulas, but they are still there. I just write the main part of the corrections. So as you see, both terms that you have here, they are an expansion in alpha S. And the dots means that you can add orders. And actually, if you look up in HDK, they have included even higher order to the one that I'm going to show you plot for right now, so figures for right now. And you see they have the expression that they have. They're just an expansion in alpha S, and they contain the dependence, of course, on the massive degrees of freedom. There is another important factor that has changed from here to there, and is the mass of the quark. Here you have a mass that I just wrote as the mass of the quark, in this case, square. And on the bottom, you have the running mass of that object square. And this is an important difference because there may be a big difference depending which kind of decay you look at. For instance, if you look at the decay of the bottom quark, there is a big difference between the pole mass of the quark and the running mass of the quark at the scale of the decay, which is the scale of M Higgs. Now, what is happening in going from here to here is the following. So you take, suppose you stay at the order that is used in this formula, which is the second one. So you had the 2 orders of QCD corrections. This is a prototype example of diagrams that you put in. So you put in the tree level, you put in the first order, which is real emissions, you put in the second order, which is real emission. And at the second order, you get also other contributions, like contributions of this kind that are still 2 loops, as you see. But they have the peculiarity of having a loop of top quarks, and this goes into the delta T that I showed you before, right? And you just perform the calculation, and at the end, you get the formula that was on the screen before, right? Now, in here, you expect, because it's a Higgs going into something colored, and because the coupling of the Higgs that you have here is proportional to the mass of the quark, you expect a lot of this correction to be reabsorbed into the renormalization just of the mass of this object. And this is precisely what happens. And that's the reason why, in the formula that we have before, this mass is a renormalized mass, and the MS bar mass that is normally used in here. And the reason why the MS bar is used as a prescription in here is just because it reabsorbs corrections in such a way that the prediction that the final result that you have is more perturbatively stable, meaning that it includes also, strictly speaking, when it's written in a factorized form like this, even higher order correction with respect to the one that you are accounting, but it makes the overall prediction more stable. And that is an important factor when you look at higher order correction, changing the renormalization scale of your process and seeing that the result doesn't change. It's a really good property, as we will discuss later on in production as well. So here is, for your references, the expression of the running mass at 1 loop, the expression of the running mass at 2 loops, or at higher orders, because these functions are not specified, and I wrote them here for your references just as an expansion in the variable, which is alpha s in this case. And as you see, the expansion can continue to the order that you have available. And HDK, as I said, I think has included till the next order right now. Here I re-emphasize the point that I just made for you. So you see, when you calculate the renormalized mass of the B quark at the mass of the B, so MB at MB, at the pole mass of the B, is about 4.2 GeV. But when you run it up to, let's say, 100 GeV, around where we expect the mass of the Higgs to be, is 3 GeV. So it's a big difference, right? So this factor, remember, it's out in front because also the coupling of the Higgs depends on the mass. It's a big multiplicative factor out in front of everything. So if you change it by a factor of 1.5 or a factor of 2, you get easily a factor of 3 or 4 difference in your decay rate. So you've got to be very careful about these things because otherwise the prediction is completely different from what you expect. There are uncertainties left, of course, and there are uncertainties that are due, of course, to alpha strong. So this will affect everything at the hadronic level, at all, wherever it appears, right? And this is cued by better determination of alpha strong, a consistent perturbative calculation of the processes that you want to consider. And the determination of the pole masses of both the charm and the bottom that, however, are reaching better levels of precision these days, such that I'm coming to the question, such that the final result will have at this point, I think the current estimate is probably 2% uncertainty, 2-3% uncertainty at most on the Higgs to fermion, so the Higgs to quark, Higgs to BB bar kind of decay rate. Yes?
What does it exactly mean when you say like at one scale the mass is 4.2 GeV, at some other scale it is 3 GeV?
What it means is just that when you determine MB at MB, you measure it to be 4.2 GeV. When you run it up, so if you assume, suppose you take this number that comes from some determination and it's a certain value at a scale MB, that's your starting point. Then you'd evolve it using a normalization group, that is what gives you these formulas, and this is what you get, okay, a 2 loop.
Physical B with 3 GeV mass.
Well, what it means is just that when you want to calculate the decay rate of a Higgs to BB bar, and therefore you want to use the expression that we had on the previous transparencies, this one over here. Here in front, after you have added QCD corrections up to 2 loop, the mass that you have here in front is not the 4.2 GeV anymore, it's a running mass. It's an MB of mu. Now, what scale to pick is your problem, right? So here I wrote it as M Higgs, because that's the scale, the natural scale of the decay, right? But let's say it's a scale of around 100 GeV. So you put you can also do the exercise of putting a mu scale here, not fixing it. And then varying the scale in a range, that is the range that you expect to be the range of a Higgs particle produced in around 100 GeV that decays. So vary it between 50 and 200 and see what happens, right? So if your prediction is good and is perturbatively good, there should be very little variation. So when we say there is, for this decay rate, a 3% error, 2% error, that's what it means. It means that when we vary the dependence, the perturbative dependencies, our prediction for the branching ratio, so for the rate, is very stable. And then at that point, you pick here, if it's a plateau, you pick a reasonable point in the plateau, and the mass of the Higgs is exactly there, and so you put the mass of the Higgs here.
So should we think of this as just renormalization of Yukawa couplings, but not, I guess, like in the phase space?
Well, this is the renormalization of the three-point function Higgs to BB bar. That's what it is, right? So you write that, and of course in there they will have to use renormalized parameters, right? So this is, now, the Yukawa coupling is in there, and at the first order it doesn't get renormalized, but at the second order it gets renormalized. So this is part of the process. So yes, you start with your Lagrangian, which is the Lagrangian of the standard model, and in particular the piece that is involved into here is the scalar piece and the coupling to fermions. And you work with the renormalized Lagrangian to get these to the order of QCD that you want. Yes?
So the effect of the quark mass being is run is in the decay factor f squared and also in the beta f, right?
In the...
So the effect of the mass of the quark. So
yes.
So,
yes.
How large is the effect due to the beta factor?
Very little. It's a very good question, actually, because sometimes it's overlooked, it is. And just perfectly right. So if you go from one mass to the other, you have to go from one mass to the other everywhere, right? And indeed, that's what is done, right? But there is very little, if in this beta Q you use 4.62, for instance, for the B, so if you use the pole mass, or if you use the running mass, you see very little because it's a phase space effect. Okay. And producing two objects that are 5 GeV or two objects that are 3 GeV each at a scale of hundreds of GeV, it's not a big difference, right? But this is a multiplicative factor. So the mass that goes into the Yukawa, it's a multiplicative factor, and as such is clearly something that makes a huge difference when it goes from 4 to 3, right? Because that's a difference. But thank you for asking, because this is a very pertinent question. Yeah, sorry.
So this beta parameter, that comes from the space decay. So it seems like the phase space shouldn't change depending on the scale, right? Because the physical quark mass is the same. So
well, but what is the mass at that scale?
But I mean, eventually, the final state, it goes showers into something with.
Yeah, but you should use the value of the mass that you have. If you are working at a given scale, you should use the mass parameter at that scale, right?
Quick question: Isn't the mass that goes into the beta not the mass parameter that appears in the Lagrangian, but rather the physical pole mass of a final state particle, which should be normalization scale independent?
Well, this is there is no really clear-cut answer to that, really, right? So this is the mass of the quark at the scale at which you are evaluating the process, right?
Well, I'm a little bit worried because the actual matrix element of the decay process should be scale independent.
Oh, yes, if you are able to calculate it at all orders, yes.
All orders, yes.
Yes.
Suppose we did. Then we have to
yes.
integrate that over the phase.
Yes, then it would be completely independent. If we did, then we would not be discussing about which mass to use, right? So it would be completely independent from whatever decision we take, right?
So the phase space does not depend on perturbation theory. It's going to be the same no matter what order perturbation theory you go.
Well, let's say that the calculation that you do gives you, let's say, this result or this result, depending on the order which you do the calculation. And in there is a mixture of terms that come. There is a factor that clearly depends on the phase space, that is this one, and there are other contributions that just depend on the corrections that you put in, right? But in there, till your calculation is done at a given order in perturbation theory, it's arbitrary what you use, right? So you just need to estimate with the impact of corrections is the largest, and then decide what to use, what is most correct to use in both places, right? So why should it be? I mean, why should you use a mass that is not the running mass everywhere? So the value of the mass at the scale at which you evaluate your process.
Think about it this way. Your phase space is for some particle that has some long life. So you can evaluate the mass of that particle in its own frame at its own scale. So the relevant scale for how heavy is my B is how heavy the B is.
But you see, till you have a scale dependence in the process, it's an intrinsic scale dependence that is not going to be removed because it's a fixed order calculation, right? So it's not at all orders. You have that scale dependency, and we can discuss, and this comes in a lot of different fields as well, in a lot of different situations, like what scale to use for the alpha S in showering, what scale to use for the alpha S in the hard cross section, what scale to use. We can keep discussing what is the most reasonable scale to use, but there is no clear-cut answer. The only thing that you can do is just to go and see what.
The uncertainties come into the matrix element squared, right? But the phase space itself should be scale independent because no matter how high an order perturbation theory I use to evaluate the matrix element, the phase space is going to be the same at all orders. So no matter what order I calculated in, that part of the calculation should be scale independent by itself.
Up to a point, because the phase space is also taking into the phase space when you go up to higher order processes, you're changing the phase space due to real corrections as well. So the phase space for your Higgs to BB bar decay becomes a phase space also for BB bar plus extra particles due to this diagram that we put in here, right? So it's not something that is completely isolated from the QCD that we are putting into the game. And these objects will talk to the phase space of these objects because they have a soft and collinear region in which they are reduced to this phase space. So, you know, it's not so clear. And these two objects, the real parts of the calculation, they all talk to the Higgs to QQ bar. And they talk to the Higgs to QQ bar because the region, there is a region of this phase space that looks like a 2 to 4 that is actually 2 to 2 where these two objects become soft or collinear. And there is a region that is actually 2 to 3 where one of them becomes soft or collinear and the other doesn't. Same for this story that you have 3 particles, it looks like a 2 to 5. But there is a region of that phase space that talks to this one. So even the calculation of the 1 to 2 process is something that fills the full QCD calculation with all the peculiarity and features of the normalization of the theory, and even of the infrared part of it, which is the one that I was just mentioning right now. So it's really not clear. I mean, it's not. This is a calculation that is done perturbatively in QCD, both in the ultraviolet and in the infrared, and there is no clear-cut answer to that.
Maybe it's also helpful to remember that bottom quarks are not asymptotic states, which means that integrating over their phase space is not entirely meaningful here because that's not what propagates long distance.
And also mention the fact that, always think to the fact that they don't see B quarks at colliders. So they see at least B jets, right? So on top of not being asymptotic states, so they even see something that is much more complicated than a B, and is all described at a given order over summing corrections. So you really have this intrinsic and physical dependency in there that you have to treat in the most consistently way you can. And there are situations like this one in which, following the question of your colleagues, it's really arbitrary if you want what you want to put in, right? Because if in here, in the calculation of the BQ, I use MB or I use MB of mu, they're all higher order corrections, okay? And then I have no way to tell you which one I should use. Wow, I didn't think it was so interesting, this slide. Okay, let's go.
The invariant mass of the B jet, would you expect to, I mean, there's presumably something, would you expect it to be MB at MB then?
The invariant mass of the B jet?
Yeah, so you sort of look at what was the originating.
No, I would not expect it to be MB at MB. I would expect it to have a scale dependence, right? Yes, yeah, yeah.
Is part of the
the normalized quark mass and sticking that into your loop correction to the vertex rather than doing a completely consistent or normalizing the vertex and the quark mass and everything else.
Okay. Now we're going to the gory details. So we won't get to cover everything that is in this lecture, but it's good. But it's a good question. So what he's saying is the following thing, I think, right? So if I had just to take this process and calculate what is depicted here plus all the similar things that are, these are just examples, right? So I would get something that is what I've written here. If I take m bar q of mh, I use the expression that is listed here at 2 loops. I expand it and keep up to order alpha s squared. That's what I would get. So when I write something in this form, it contains more than just order alpha s squared corrections. It contains also something that you see in this mq squared of m Higgs. If you use the formula that is over here, and you use the expansion for f, it's written as a sort of a polynomial in the numerator and the denominator. You have terms that, if you keep expanding, are higher order, right? So when I put it in front of, when I plug it in front of everything, so when I plug it in here, and I multiply by a parenthesis that also contains order alpha s, I pick up also alpha s cubes from there, right? So he's saying the scale dependence that you see is due to the fact that you like to have a lot of factors out here in front as a sort of renormalization of the mass, but in so doing you introduce more than your fixed order. Well, no, it's not, well, it's part of the leftover scale dependence. So you have a choice. You can use the pole mass up here and leave all the terms that have been resummed into the renormalization of the mass in this parenthesis as part of the delta QCD. And that's a perfectly fine choice, right? Or you can do this, and you pick the one that gives you more stability. And you know that either choice is as good, and the reason for that is just that the difference is higher order. So as far as that difference is not bigger than the uncertainty that you see coming from scale dependence, you're fine. So no, the scale dependence is just coming from leftover higher order terms that are not included into here. And what is included into here are the piece of those terms, the part of those terms that are the most important one to keep the scale dependence under control. And then you let the scale vary, and you see within which range this rate varies, and it's very, very small. And therefore, you convince yourself that this is the best way that you have to write it. But it's ambiguous, right? So it's not clear-cut. You can do one way or the other way. But it wouldn't change more than 1–2% if you so do, when you have included high enough orders. Because, of course, you push. This would be a very dangerous game to play at 3 level. So if at 3 level I use one mass on the other is a factor of 3, right? So it's a very, but the more orders you put in, the higher you push the difference between, the higher you put the ambiguity of using a scale or the other, and that's your point of doing it. And then your prediction is very stable, and then you can do what you think is more elegant or convenient in your final expression for the rate.
And then, but if you did it sort of this fully consistent way, would it be unambiguously the scale that you should evaluate it at is n Higgs, but you never really have the full mass of it be anywhere exactly as that exact expression?
Well, the choice of the scale is what you like to have in there, right? And it shouldn't depend much on that scale by the time, but of course what you choose is a scale that is reasonable. It wouldn't be reasonable like when you take a collider process, it wouldn't be reasonable to put alpha s at a scale of 5 GeV, right? Because, and clearly you would see that the perturbative behavior of your cross-section completely wild at that scale, but that's not the scale of the strong interaction you're trying to reproduce. And here for the decay of the Higgs, again, it wouldn't make sense to look at how it behaves at a scale that is not the Higgs scale, right? So, let's see. Here is the other example that I wanted to give you because it's a really interesting one. And we see in here something that we're going to use also later on in production when we look at this process in a mirror, and it becomes the production of a Higgs via gluon fusion when you revert this diagram. So the decay of the Higgs into gluon per se as a matter of fact, is an important decay, but as you may imagine, not so important. And the reason why it's not so important is because, well, if you produce a Higgs at a hadron collider and you let it decay into gluons, good luck to see it, right? So because, yes, it will be just 2 gluons out of zillions, right? So, but because we are going to see this as gluon-gluon fusion into Higgs, and it has exactly the same characteristics, let's have a look at what goes into the calculation, this time briefly, because so that we can move on. But the main point is the following one. So, this is not a tree-level decay, this is a loop decay. And because of the Higgs, it happens through a loop of heavy particles. So it's completely dominated by the top quark in the loop. Now, it will be also dominated by any heavy degree of freedom that couples to the Higgs in extensions of the standard model. So there is in these also the possibility of new physics, but we stick to the standard model. If you do this calculation, which is a one-loop calculation, this is the expression that you get. And here you have all the details of what the calculation should look like. So it's proportional to the mass of the Higgs, and in here you have the proportionality to the mass of the heavy quarks, starting from a direct proportionality that is out here in this tau factor, that is proportional to the mass of the heavy quark square. So you can try the calculation and see this is what you get. But because of the fact that the contribution, the main contribution, the only contribution that you really want to consider in here is due to a heavy quark, so it's due to the top quark, this is also a perfect place where to apply what we call low energy theorems in general. So theorems in which you reduce basically this coupling to an effective coupling. You squeeze the loop at the top to a dot because of the fact that you're looking at heavy degrees of freedom in a sort of effective field theory approach. So now you may be thinking, well, it is going to work so well because the Higgs is not so much different from the top. Well, it does. It's different enough that it does, due also to other characteristics of this process that I will point to you in a second. So if you had to calculate the loop correction to that process, that I wouldn't really mind if it was just for the decay, but that had to be calculated for the production process, as you will see tomorrow, then this is the kind of things you get into. And this is just one loop of corrections, because the process starts at one loop. And we know that whenever gluons are involved in the final state, typically one loop is not enough. So it would be really tough to go and have a stable prediction for these objects. But if you can squeeze this loop to a point, well, then it's a regular vertex, and then you can go up in order more easily. And this is precisely the way it works. So the calculation has been done at this order, so at one loop, so what we call next to leading order, both in the full theory and in an effective theory, in which by squeezing this interaction to a point effectively, you can see that the decay branching ratio becomes the decay branching ratio at the tree level times just the correction factor that you can easily calculate it. And the reason for that is partly due, mainly due, as a matter of fact, that this process is dominated precisely by soft and collinear dynamics, so by extra radiation that is emitted past the tree level, and this is due to the presence of gluons in the final state and to the structure of the phase space of these objects. And because of that, the soft stuff that you produce and that dominates the evaluation of the cross-section is soft, right? It doesn't really know and doesn't really see the loop of tops. So it doesn't really see how the Higgs is coupled to the top and the top decays into gluon. And so if it's extended or if it's contracted to a point, if an effective vertex, it doesn't see it, and it works as the same way. So this is a plot that shows you how well it works. So this is the real calculation, and in here you see some features that you can understand. So for instance, you can see the quark top threshold coming up here and giving an enhancement and then dying out because of phase space reasons. And then you will see on the same plot, you see the dash curve that is just the formula that we had on the previous transparencies. So it's just the leading order multiplied by a factor, calculated in the effective approximation. And you see, this is not a log scale, this is a linear scale. So if you look at this curve, say, oh, they don't agree at all, because you're used to log plots, right? But this is a honest plot with a very expanded scale over here. So in a region where you would expect it to work, which is down here, it works decently well. It works pretty well, and it's more than enough to give you a good estimate of higher order correction if you use it. So because of this, the calculation has been worked out to n and LO, and actually this day even one order more. And what you see is just that the first step from the tree level to the NLO, it enhances the rate by 60 or 70%. And you say, wow, I cannot stop here. I need to find a way to add orders of QCD because it may be that this cannot be calculated perturbatively at all. And you have to check higher orders to see if the perturbative series converge. That's the only way we have to see if the perturbative series converge or not. So the fact that due to the effective theory, you can go higher order and you can calculate the NLO is very important because then you see that the next step only at 20%. And then you feel much better. And the same we will see for glue to Higgs, where things, of course, have been beaten to death far past this point because it's so important in production, contrary to decay. So to this day, this is the most uncertain decay still, because there is still an order of 10% uncertainty on this decay. But luckily enough, this is not the one that we use the most. So that 10% is effective Higgs physics, not for the decay, but for the production, when you mirror the process and you make gluon into Higgs. There is so much, I mean, this process of gluon coupling to Higgs has been used so much and worked out so much that is actually, there is a lot of interesting physics to be discussed there. And let me just mention this to you and then we can move on. One of the interesting things that has been brought up many years ago at this point, but that was very successful in working out the physics of the pairing of a Higgs to gluon are what are called low energy theorems. And they're based on the observation that in the limit of the Higgs momentum going to zero, if you take either a fermion or a gauge boson propagator and you had a Higgs, like to make a Higgs fermion Higgs vector vertex, basically is like substituting in your calculation Ni with Mi times a factor that is 1 plus the Higgs over V, right? So H over V. This in your Lagrangian. This is precisely what you have to do. And then what you do is just that based on this observation, and you can just work it out on a piece of paper, very easy to see. So based on this observation, then what is normally done is just to consider the Higgs on shell and to take the limit of p Higgs going to zero as a limit of small m Higgs, which is precisely the same spirit of the effective theory that we had before. Right? So because of that, because taking the limit of small m Higgs is just taking the limit of large m top in that diagram. It's exactly the same, right? Saying that the top is much heavier. But because of that, if this is indeed the only change that you have to have in your calculation in order to add one Higgs vertex, you can calculate correlation functions with the insertion of a Higgs in terms of correlation functions without the Higgs, taking just the derivative with respect to the mass of the particle to which the Higgs is coupled. So this very nice property work that in the limit of small Higgs momenta, that means in the limit of small Higgs masses for a non-shell Higgs, the amplitude for a process that includes a Higgs in the final state is calculable from the amplitude for the process that does not include the Higgs in the final state, taking the derivative with respect to Mi, where Mi is the particle to which the Higgs is coupled. And this makes your life so much easier because you can calculate, for instance, a 3-point function with the Higgs in terms of self-energy without the Higgs. And calculating, and this goes on to the loop order, so calculating 2-loop correction to a self-energy is much easier than calculating 2-loop correction to a 3-point function. And that what you have to do is just to do the first and then take a derivative, which is a much neater things to do. So all these methods have been used and have been developed to study a decay like Higgs to glue and vice versa, the production glue to Higgs. And these kind of things are included in programs like HDK to get you the branching ratios. This is just for completeness. I also list you what the expression for the decay into gamma gamma and to Z gamma is, and we just move on. Now, so we have seen a first impact of the quantum structure of the standard model in just decaying, in just determining the decay property of the Higgs. Big impact in the most relevant decay mode and in decay modes that are interesting to study for future purposes. So another place where this has a big impact is, of course, electroweak precision fits. Why? Well, because they are the full quantum structure of the standard model is at play. You measure all the possible electroweak observable, and this program has been carried on successfully at both the lab mainly and the Tevatron together. And you identify what are the best measure parameters that you have in your model, and you give them as input, and you constrain everything else. Well, first of all, you check the consistency of your model. In your model, you still have one unknown, which is precisely M Higgs, so you use it to constrain it. It's a beautiful program that works very well, just because the Higgs, the scalar sector of the standard model is so minimal and so well constrained. So take it, as we said at the very beginning, as a very nice exercise, because it's here where you learn which kind of things you'll have to do for any new physics by the time it is better constrained. So the reason why it constrains the mass of the Higgs is because, of course, as soon as you decide what the scalar sector of the standard model is, and you treat it at the quantum level in the standard model, he will contribute to the corrections of all the parameters of the Lagrangian of the standard model, so it will contribute to the correction of the masses of the particles that are in the standard model and the couplings. So in particular, it contributes to the mass of the W and the Z, and to the renormalization of these masses. It contributes, however, to many quantities that are important for the standard model, for the constraint of the standard model, like the famous rho parameter, the ratio between the two masses, in a logarithmic way. So it's not a big effect, it's a small effect. So in order to see it, you really need to go to high precision. So you cannot play this game on the back of the envelope. You really need to have, but this has been worked out over the past several years. It's lab physics, mainly this, because this was part of the lab program. And the plot that you're used to, that I just give you here, is the result. So let's understand the plot that we have over here. This is one of the most updated one. This is the most updated one, actually. So it's 2010. There is nothing new done in 2011. All this information and much, much more you can find on the Lab Electroweak Working Group homepage, where all the last fit are reported with all the details. But let's see what you have here. So on this plot, you have the correlation between M top and MW that are both measured, and the measured are here. So coming from the Tevatron with a very high precision. And of course, they are correlated, and the correlation depends on the mass of the Higgs because of what we have seen on the previous transparencies, because the Higgs happens appears in the quantum corrections to a lot of electroweak observables that also depends on MW and M top. So the red curve and the blue curve are typically given to see how the situation has changed in going from lab 1 to lab 2 and the Tevatron that is nowadays, what we have nowadays. So a big uncertainty has shrunk to a very small uncertainty, and the green band that you have here represent what should be, where the mass of the Higgs should lie in going from 114 to 1,000, basically. So in going from the experimental limit to a reasonable bound of 1 TeV, in order to be compatible with the corresponding mass of the top on the x-axis and the corresponding mass of the top on the w-axis. But we know the mass of the top and the mass of the w, so here is where it should lie. Right? So very, very, very little space left for a Higgs of the standard model kind to fit the electroweak picture. Right? So definitely what we can get out of here, of course, it is a statistical game. So we may discuss over and over and over if this has to be taken very, very, very seriously, or if we just have to take it as an indication. But even if you want to take it as an indication, what it's telling you, and here are the numbers that come out of the statistical exercise, is just the standard model definitely prefer a light Higgs, very light Higgs, right above the experimental bound that has been fixed by lab at 114 GeV about. And we nowadays have another exclusion bound, which is the exclusion bound coming from the Tevatron that excludes the region between 158 and 175 GeV. And we'll see tomorrow which kind of uncertainty there is on this and which kind of discussion we can have on and how much we need to rely on that exclusion limit. But let's not consider the intermediate slice that is cut off at this time by the Tevatron. There is this lower bound and the Higgs has to be light. So this is something that we need to take very, very seriously, and it's an amazing exercise if you think through, because it's the prototype example of how much the quantum structure of a theory can tell you about new physics. It can tell you a lot. Now, there is more that we can say, and there is more, although it's not as precise as what we have seen on the previous plot, but they're very important indication, and I want to come to this because it's important, I think, to see how just studying a particular assumption for the scalar sector of the electroweak theory, and assuming a very particular way for the realization of the electroweak symmetry breaking, still, even if it's not the right thing, just studying it will tell us something and tells us something on where to expect new physics that can also be completely different. So if you think the standard model as an effective theory, as we all think, that will break down at a certain scale, and you realize the standard model including the scalar sectors that we have discussed yesterday, then you can think that, oh yes, Higgs physics depends just on one parameter, as you told us today, the M Higgs, but actually depends on two. It depends on M Higgs and on the scale of new physics, because that is the fundamental scale in which the whole picture breaks down, right? So, and because the electroweak symmetry breaking is so intimately related to new physics, there has to be a sign of that in the way the new scalar degrees of freedom that we have introduced into the theory behaves and contributes to the theory itself. And in fact, there are bounds that we can get from there, and there are very interesting indications that we can get from there that are mainly based on consideration of unitarity of the theory of the whole standard model, consideration of triviality and vacuum stability of the scalar sector of the standard model. So let's look at those three topics first, and then come very briefly to comment about fine-tuning, which is another important point that is normally discussed in talking about the scalar sector of the standard model. So, so unitarity, you know what we're talking about. So we're talking about the fact that the scattering, like in this example, of the longitudinal components of the gauge bosons of the standard model grows with energy, so violates unitarity. And this is somehow rescued precisely by the same degrees of freedom that give a longitudinal mode to the gauge bosons, which are the scalars that we have introduced in the standard model, because when you introduce the extra diagrams into VV scattering that are due to the Higgs bosons, that bad energetic behavior goes away. But at the same time, now the cross-sections for scattering of longitudinal gauge bosons depends on the mass of the Higgs, precisely because it's one of the contributions. Now, there is a very neat way of calculating this scattering through the equivalence theorem that makes your life much easier, because you can show through just looking at the word identities of the theory that the amplitude for the scattering of the longitudinal degrees of mode of the gauge bosons can be calculated as the amplitude for the scattering of the corresponding Goldstone bosons, as you expect, because you remember the example yesterday of how the phi 2 that we had in our simple example was so very much entangled with the longitudinal degrees of freedom of the gauge boson to the point that its propagator had the mass of the A inside, right? So this is not a surprise, but you can show it just through word identities. So if you use this little property to calculate, for example, the amplitude for scattering of W plus W minus into W plus W minus longitudinal, right? You will see that it has this expression. So, and that is, if you calculate on the side of the one for scalars, for the Goldstone mode, you see that it's precisely the same, and just you need to sum this term with that term and this term with that term to calculate that and to see that it's true. So if you so do, you, yes?
Just a question about the equivalence theorem. Is that equation a very tough one? A gauge invariant statement? Because I would work in the unitarity gauge, I wouldn't have any Goldstone bosons. Or is the left-hand side evaluated in one gauge and the right-hand side evaluated in another gauge? What's the detail on that?
No, of course you have to you have to work in a situation in which you do have Goldstone bosons, and in that situation the two are. But I think it's a gauge-independent statement because it comes just from the word identities of the theory. So now, once you have the, there is a way to, you calculate your amplitude. Now, just look at the problem, just look at the same amplitude as written in terms of partial wave decomposition, right? So you organize as a quantum partial wave decomposition. And you calculate the cross-section here written as partial cross-section d sigma over d omega. You calculate your cross-section integrating over d omega, and you use unitarity. So here is where unitarity comes into play. In order for unitarity to be enforced, you have to have that the cross-section for the process that you are considering is equal to twice the imaginary part of the forward cross-section. That is what the theta equals 0 means. So if you enforce this condition using this A plugged into here for theta equals 0, PL is equal to 1 for theta equals 0, you simplify what's simplified left and right. This is what you get. And now you rewrite this expression as the real of AL squared plus the imaginary of AL squared, you get an equation. So, and that's where the bound is coming from. So what I'm saying is just that the equation over here, right, becomes the real part of AL squared plus the imaginary part of AL square equal to the imaginary part of AL, right? And you can rewrite these as the real part of AL square plus the imaginary part of AL minus a half square equal to 1/4, right? So it's just a little trick that you play on that equation. And from here, you have two ways of reasoning. This is the most conservative bound that you can get. So you see, you can even represent these. You see what this is? It's a circle, right? So if you write real AL, imaginary of AL, this is your circle that you get. There is a half, right? And then the phase between the real and the imaginary part is what drives you around that circle. So the bounds, the most conservative bounds that you can get is just from imposing that, of course, from this picture and from this equation, the real part of AL, which is the only one that you have at tree level. The imaginary part of the amplitude comes in at the loop level, right? The real part of AL that should also be the dominant part for the theory to stay perturbative has to be smaller than a half, right? Because it has to say that this is 0, the imaginary part is 0. The other, a little bit more relaxed bound that I'm not using here that you can use is the fact that the imaginary part is small because it comes in at higher order, it comes in at the loop level. So you can use, instead of this bound that we use here, the fact that the imaginary part has to be, when the imaginary part is of the order of the real part in this equation, you have the first breakdown of your theory. And the mass of the Higgs that correspond to that is an upper bound on the mass of the Higgs. And this is as to say that you look for phases in here that are of the order of pi over 2 of pi. So when you see when the imaginary part is of the same order as the real part, or even bigger than the real part, it's a clear signal that your perturbative expansion is breaking, and is so because of the fact that the imaginary part comes in at one loop. So, going back to your amplitude and calculating the dominant contribution, which is the S-wave contribution, the A0, you get a bound on the mass of the Higgs because you calculate A0 from this expression here using the orthogonality of the Legendre polynomials. So you take an integral of this object and you calculate A0 for the omega plus omega minus into omega plus omega minus, which is as to say W plus W minus W plus W minus longitudinal. You get this expression. You take the limit for energies much bigger than the mass of the Higgs, which is precisely the regime in which we are working, right? We are considering here, and you get this expression that depends on the mass of the Higgs. Now, imposing now that the real part is smaller than 1/2, it gives you a bound on the mass of the Higgs that is of the order of several hundred GeV, so the order of the TeV. You can turn these, so this is quoted for the process that we have been discussing. Then you look over all the possible scattering, longitudinal scattering that you can think of. You do the same exercise, you pick the one that is most constraining. And this one, WW into ZZ, turns out, well, actually a linear combination of twice WW plus ZZ turns out to be the most constraining one and gives you this bound on the mass of the Higgs. You can turn also things around and think of what happens in the opposite limit. So in the limit of m Higgs squared much bigger than S. And what does that mean? So what that limit is the limit in which you are at a scale in which you don't see a Higgs, right? So you are in a theory without a Higgs. So it's telling you something about where to expect new physics, basically, because the Higgs is not there, right? You haven't seen it, right? And well, if you turn things around and you work in the opposite limit, so in the limit of a Higgs that is past the energies you're looking at, then what you will see from the previous, if you take just the previous equation and you take the opposite limit, you get this result. So you see that it's proportional to S, as it should, because you don't have a Higgs there to solve your unitarity problem, right? So you still proportional to energy. We go back to the original problem. So you go back to the problem of some other physics will have to solve the unitarity problem in the standard model. And where does it have to be, that new physics? Well, you take just from here, imposing a unitarity constraint, so imposing that unitarity is somehow solved by something else, you will get a bound of around a couple of TeV at most. If you use the other kind of unitarity constraint that I was referring to before, so if you impose this phase delta, so the relation between real and imaginary part is such that the imaginary part cannot be bigger than the real part of the single partial wave amplitudes, well, what you get is something that is more of the order of 3 TeV or something like that. So it's telling you that if the Higgs is not there to take care of unitarity and something else has to jump in order to save the unitarity of the standard model, that is the scale at which it has to happen. So it's very exciting because it means that all these we learn just studying this very simple physics, right? And this is telling us that we are really looking in the well, we are here with machines that are looking at that scale of energy, and that is the scale of energy where we do expect things to happen. Yes?
So here, when you see unitarity, it is G-level unitarity, right? So here, loop contribution is not there. So my question is, isn't that possible, taking into account the loop contribution, can push up the new physical excitation to higher orders? So, higher energies. So, I mean, if you take into account the loop contributions,
well, that goes into the discussion that we had, that we were looking at before, where there is a contribution to the imaginary part of the amplitudes, and in principle, it has to be a loop contribution. So yes, it can change slightly, but it doesn't have to be a major change, like, precisely for that, because otherwise you're breaking the perturbative structure of the theory. When that happens, it's breaking the perturbative structure of the theory. So. Now, let's move on to the second, yes.
Can I think of the breakdown of perturbation theory for double scattering as strong coupling of the Higgs, so the Boson modes of the W?
Yes, yes, you can.
I guess that would seem to indicate that, we say strong coupling is the reason things look like they blow up, but you don't include all the loops, and you can't include all the loops.
So that you see a failure of the perturbative approach, right? So you're going from a weak regime to a strong regime, from a weak coupling to a strong coupling. So you're changing to something else, right? And this is telling you when the kind of calculation that we are doing here, which is perturbative, where will it fail if nothing else comes in at that scale?
Comparing the bounds from unitarity to those from triviality and vacuum stability, and it's looking like for example, if I
you're reading ahead.
Less than 780, it doesn't look
That's why you shouldn't have transparencies before the lectures, because you're looking ahead. Okay, but just so yes.
So it doesn't look like it's really putting much of a bound on the Higgs mass, because triviality is already coming in much before that. So when you cut off right, if you could go to a couple slides before to the Hubble plot, yes, that one.
Yeah.
And if you draw a line from unitarity down, which is at like 780 or 870, it's like way up there above the triviality curve. And so, I mean, it doesn't look like the unitarity is really helping us here in terms of putting it down in the Higgs mass.
Well, but I think it's very interesting on the other hand, from the second point of view. So the point of view of looking at unitarity as an indication if the Higgs is not there, right? So that is, I mean, this is a fundamental problem that you have to address. It's not really constraining, well.
Because, I mean, that curve, the upper curve, is essentially telling us at what point is the theory going to be non-perturbative. Because the unitarity is setting a mass.
Yeah.
But because the unitarity constraints are setting a mass that's above the perturbativity scale.
Well, at least they are compatible, which is a good thing, right?
Okay, all right.
Yeah. So, okay, let's come to what he was talking about. So triviality. Oops. So what triviality is what you have in mind. So we are adding to the theory of the standard model a lambda phi to the 4th theory, which is the scalar part of the Lagrangian. And if you take just the lambda phi 4th of the theory by itself, you know what the beta function of the theory is positive, so the coupling grows with energy and decreases with energy in the same way, right? So it cannot be perturbative at all scales, and therefore the issue of triviality. But in the standard model, you cannot look at that as isolated. It has to be looked at together with the full structure of the standard model. And when you look at that with the full structure of the standard model, because the scalars are coupled to everything else, the behavior of the quartic coupling in the scalar part of the Lagrangian is much more complicated. And it depends on lambda itself, but it depends on the gauge couplings, it depends on the Yukawa couplings, and in particular, of course, on the most important Yukawa coupling, which is the Yukawa coupling of the top, with all the arbitrariness that goes with that. Right, so we don't really know that it has to be like that. But if we assume the standard model in its prepared package, this is what the beta function for lambda looks like. So you have indication the upper and lower curves in the plot that we just looked at comes from precisely the beta function of lambda into different limits. So the first limit is for large lambda, and large lambda means large MH, precisely from the relation that we have here on the blackboard. So in the large lambda regime, you look at this equation, basically you are back to the situation of a lambda phi to the 4 theory, because these are the two terms that survives, that are most important, in particular the first one, which is positive, as a positive coefficient. So you solve the equation at the first order, this is what you get. You need to impose a cut on lambda in order for this denominator not to go to 0, and the coupling not to blow up. And that's precisely what you do, and impose that lambda q is finite, so it doesn't blow up, gives you a bound on M Higgs. And this is the upper curve on the plot that we had before, which is a band, just because you have corrections to that. You have error, a theoretical error on the parameters that you're using. Now you go to the other regime, and you hit an issue of vacuum stability. And what this is just that if you look at small lambda, that also means small M Higgs, what you get is just that the dominant terms is not, of course, the lambda term anymore, but the dominant terms in here are terms that are proportional to the other couples, in particular to the Yukawa at the top, which is the biggest one. And so if you use the asymptotic expression of the evolution equation that we had on the previous transparencies, this is the solution that you get. And in order for the coupling can get negative, so in order for not to have a potential that can grow infinitely in the negative direction, so not to have a problem of vacuum stability, you have to impose again a bound on lambda, so you have to require that lambda is positive at all scales. And this gives you a constraint on M Higgs, when in this equation you use lambda as lambda and MV is set at the scale of M Higgs. So this gives you the lower curve on this plot. So this is from vacuum stability, this is from triviality. And as we have just discussed, thanks to the question of your colleague, the issue of unitarity is just the issue of compatibility with what you get from the other bounds in the theory. Now you look at this plot, and before we move on to the last consideration, you see that it's really instructive. And it is instructive why? Well, because you see, we have seen from, let's pick electroweak precision fits, that the standard model really pushed for a light Higgs if that is the reason and that's the origin of the breaking of the electroweak symmetry in the very particular form in which we introduce it in the standard model. Well, light means around 100 GeV, so we are here, right? And you see, if you, including also the errors that we have on these bounds, if you draw a line here, you hit this curve a little bit above 1 TeV, so in the TeV area, right? And that's really interesting because it's telling you precisely what we have already seen from as an indication, in particular from the unitarity discussion, the new physics for a light Higgs is expected from the whole theory to make sense, from the whole theory of the standard model to make sense in the TeV region. So the last thing that I wanted to discuss with you is the issue of fine-tuning. Okay, issue of fine-tuning is what? Well, it's one that you know very well, at least for everyone working in beyond the standard model physics. This is always the point that is made in order to say, well, the scalar structure, the scalar sector of the standard model cannot be the way it is. It's not the end of the story. Well, no, that is not the end of the story. We clearly know that. But why are we so sure that it's talking to the ultraviolet completion or whatever theory we have beyond the standard model? Well, in a way, it's a problem that goes with scalar masses, right? So scalar masses, like the mass of the Higgs, are renormalized by quadratic terms. So there is a fundamental difference between the renormalization of a fermion mass and the renormalization of a scalar mass, if you think it through, because the renormalization of a scalar mass, it's always proportional to the mass itself and log of the scale. So if you take the renormalization of a fermion mass, you will always get something modulus, the prefactor that depends on which kind of correction you're putting in, it will be proportional to the mass of the fermion and then to logarithm of the cutoff over some scale parameter. That could be the mass of the fermion itself. And this is because, well, there are symmetry reasons for this, because if you set the mass of the fermion to 0, you recover Carrera symmetry in your theory, right? So whenever something like this happens, so whenever corrections go to 0 together with the mass of an object, there is a symmetry reason. But this is very important because it gives you a good feeling about the fact that the renormalization, no matter how large the cutoff of the ultraviolet completion of your theory is not going to change the mass pattern enormously, and you don't have to fine-tune. The correction are not going to be, if the masses are small, because of this MF factor, the correction are not to be huge. But for a scalar, that can happen. And it can happen because the corrections are quadratic. And therefore, in order to get a value of M Higgs that is of the order of 100 GeV, depending on what ultraviolet completion you choose and what is the scale of new physics, you can have huge fine-tuning there. You can have to compensate for the large corrections that you get. So the theory is perfectly renormalizable. It's a lambda phi 4 to the theory, so we know it's perfectly renormalizable. So you don't want to say something that is, so you may be there wondering what's the problem. But the problem is precisely the one that I just say, two large corrections. Right? Now, so there is fine-tuning required, and people don't like fine-tuning, and therefore they see in these the fact that somehow we have to rephrase what we have to find extensions of the standard model that have a better way to deal with the problem of fine-tuning. And the MSSM is a typical example for that. It's a better way to look at the problem, both because the sign of the mu square that makes the whole things happen is induced dynamically, and it's a better way to look at things because we think that we need less fine-tuning because the symmetry that we introduce is already something that allows for the cancellations that needs to take place in order not to have a fine-tuning in your theory. So there is a more general way of looking, another way, or a more general way to look at the problem, and which is, well, since the mass of the Higgs is directly related to the mu square parameter, if we look at the renormalization of this parameter, remember that we talked yesterday about the renormalization of a theory with spontaneous symmetry breaking, and how it all boils down to the renormalization of the mu and the lambda in your theory. So if you look at the correction to the mu parameter in a theory that has a ultraviolet cutoff, and is therefore the theory that will bound the electroweak theory in the standard model from above. You can organize the correction to the mu parameters into a series of terms that of course depends on the scale of new physics. They have coefficients that will contain inverse powers of the new masses that are coming in, and they are proportional to logarithms of the scale of new physics over the scale in which you are evaluating the mu parameters. Now, the best of all fine-tunings will be for this correction to go to 0. So to set all these terms just to 0. And this is known as Velman condition. Now, of course, this is over-constrained, because if you do it from n that goes from 0 to infinity, you don't have parameters enough in there to solve these equations. But you can still get indication from here if you just keep a few terms, assuming that higher order terms that you put in will be less and less relevant, right? And if you just keep a few terms, you get a bound. You can even relax this condition a little bit further and not impose that it's exactly 0, but it's small. So that the fine-tuning is small. It's not 0, but it's small. And if you use this condition and you do the little exercises knowing the coefficients that are known from calculations, right? This goes back to the calculation of the effective potential that we discussed yesterday. And when you have calculation of the effective potential at a given order of loops, you do have a calculation of mu bar at that order of loops, so order of h slash. And if you look at the numbers that you get, so the value of lambda for which your model can live without not too much fine-tuning, you see that it improves going up with the number of terms that you had in your effective potential. It tends to flatten out if you had more terms. So it tells you that the issue of fine-tuning, after all, is not so dramatic, right? So meaning that, and it's in any case compatible and somehow, yes, it can be addressed into theories that represent the ultraviolet completion of the standard model, again, in a range that goes from a few TeV to a few tenths of TeV. Yes?
So the corrections of talk that you have for the Higgs, this is obviously using a cutoff.
Yes.
If you use DIMREC, then how do you see that there's a quadratic term?
No, that's the thing. I mean, that's you would see it in terms of poles at that point, right? So if you use dimensional regularization, right, and the leftover will be just the finite terms. This is done to show you. I mean, if you use suppose, I mean, you're treating the standard models. That's what I was alluding to. So the lambda 5 to the 4 theory is a perfectly renormalizable theory, right? But what is the meaning of renormalization really there? So the meaning is just that the standard model is an effective theory, and as such, we want to rephrase things in terms of an effective language. So there is a theory that is coming in at a higher scale, a scale lambda, and is correcting the physics of the standard model, right? So the best way to look at that is really with the cutoff, right? Because there will be a theory beyond the standard model that is a theory that has more degrees of freedom, and the real renormalization you want to address is the renormalization of that theory. As far as the standard model goes, physically, from a physical point of view, it really is a model that has an ultraviolet cutoff. Now, is this ultraviolet cutoff having an impact on the physics of the model itself? Yes, of course, it corrects things here and there via logarithmic correction and whatnot, right? What impact does it have on the physics of the Higgs boson, or the physics of a scalar in the standard model? A big impact. A huge impact, as we see here. An impact that we don't like particularly because we know that the mass has to be light. And in principle here, depending on where the ultraviolet completion is, it may have to come out with a cancellation between a bare mass, and which you may tell me, but the bare mass can be anything. Yes, it's just perceived as not elegant when this happens because of the, and it's debatable, I agree, right? But because of the argument that I was giving here for the fermion mass, that for fermions you never have to get into this debate, right? So, to conclude this lecture, I just wanted to leave you with the example of physics, because what have we done? We have looked at the quantum structure of the standard model in the gory details to see how many indications we can get of what are the properties of the physics that should break the electroweak symmetry have to be. And we have used the simplest possible option, which is the realization of the electroweak symmetry breaking via Higgs mechanism with just one complex doublet as a prototype, as an example. But then we have looked at it from so many different points of view before getting what we'll do tomorrow to the phenomenology of this object, to learn to be sure that we really understand how much information this approach is giving us on the electroweak symmetry breaking, on the breaking of the theory. Now, from our discussion, it comes out from many, many different points of view that there has to be new physics. If we find the Higgs or not, there has to be new physics, because that object may also be a scalar degrees of freedom of something else and just play the role of a Higgs physics at the effective scale of the standard model, okay? And for many, many, many indications, we have seen that this physics has to pop up at the TeV, in the TeV region. Do we have examples of new physics that pop up at the TeV, in the TeV scale? Yes, we have many, right? And the first one that I give is the canonical one. And it's also the one that have been probably studied the most because it's very well defined, very well constrained, and it's based on very solid, and solves and addresses many of the problems that leave us with a sort of sour taste when we deal with the standard model. Starting from why, even it's a model in which we still use a Higgs mechanism to break the electroweak symmetry, but for instance, the sign of the parameter that drives the electroweak symmetry breaking is dynamically changed, right? So we don't have to impose the mu square is small. We don't have issues of fine tuning and so on and so forth. And it's also a model in which corrections have been studied to a good level of precision, such that we can look at the behavior of how compatible the prediction of the theory are with the electroweak fields, which is a test that any theory of new physics will have to pass before we can say it is a good or a bad ultraviolet completion of the standard model. And so I have more slides on Susie on the MSSM after this one that we are not going to look at, but you have it in your transparencies. And it's just for your reference because many of you will know that by heart. But if you don't remember why you have, for instance, many different Higgs bosons, why you have two neutral scalar, one neutral pseudoscalar and charged, look at the next pages and you will see it derived for you. And you will see which kind of bounds you have on these masses. So you will see, for instance, that in the minimal version of a supersymmetric model, you do have a light scalar Higgs. a Higgs that can be even lighter than the scalar Higgs of the Standard Model, and for which the 114 bounds do not really hold, because lab searches have much lower bound for the Standard Model, for the neutral Higgs of the minimal supersymmetric Standard Model. So here is the mass spectrum summarized for you. This is the light Higgs I'm talking about. This is its heavier partner, and then you have the other pseudoscalar and charge into it. And this is an analogous, again, a plot in MWMT, exactly the analogous of what you saw for the Standard Model, but including the MSSM. And as you see, these are the 68% and 95% confidence bounds. And this is what has been obtained with lab 2 and TV. So the blue one corresponds to the one we saw on the other plot. It's exactly the same curve, just plotted in a slightly different way, depending on the scale that you have on the axis. Then you see two more curves. So one that is what is projected by the time we'll have LHC data, and we'll combine Tevatron and LHC data. And in the very, 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 very future, what could happen if we have a high energy linear collider that will be much more precise machine. But this is not the point I want to make here. So the point I want to make here is just, you see, the Standard Model, and this is precisely what we saw in the other plot, has a bare compatibility with the electroweak precision contour, right? So with the precision fit of the electroweak data. But a model of new physics that comes after 1 TeV or 2 TeV that doesn't have to be the end of the story, but just an example, right, that I give you, that has been studied at an equal level of precision can be a better choice. Because when you see it here, of course, there has been parameters that have been chosen, there has been assumptions that have been made. I'm not saying that this is, you know, the story. It's just an example. And things will have to be changed depending on what we see at the LHC that will tell us what is the right scenario to consider. But it's possible. So it is possible to have new physics that satisfies all the constraints that we have seen before, that is exactly where the theory tells us that it should be, and that is compatible with what we already know. Okay, that is an example. And this is what in a typical MSSM model, you can get at a glance for the mass spectrum. So these are all the other particles that are there. And why do I put it here? Well, because the two things will have to go together. So, of course, we do not expect information on the scalar sector of a theory in isolation. And we won't be able to say anything if it's not Standard Model Higgs. And even if it's a Standard Model like Higgs, we won't be able to say anything if we don't see anything else, right? So predictions like this one, they always have to go together to any plot that shows you what the behavior of a scalar theory, of the scalar sector of a theory has to go. And the LHC will have to test these. And by the time we can choose between left and right, we would have made a huge step forward in that direction. So these are the transparency that you look by yourself. And this is just, I put it in as the last example of another example of beyond, which is a much crazier kind of example, right? So it's an MSSM, it's still not an MSSM, it's a supersymmetric model, but where the Higgs is a composite. And it was, that's what it's called, and it's called fat Higgs, right? Because of the fact that you avoid the lightest scalar that they come up with, and is shown in these three possible spectra that can come up, is always, is this little H0, it's always heavier than what you get in a minimal supersymmetric model. And it can be useful to have the possibility of having something that is above the experimental bounds, right? And it's also something that relies on very different assumptions, because the Higgs is not a fundamental, it's a composite object. The Higgs can be a composite object in many different versions of new models, or models of new physics that have been proposed, starting from all the versions that impose other global symmetries that then see the Higgs as a sort of Nabu-Goldstone bosons and so on and so forth. So this is very much on top of a lot of other ideas, very much a prototype example of a lot of other ideas that can predict a scalar sector that is different from the sector of the Standard Model, very different from the sector of the Standard Model. But when you look at the fit of the electroweak data, that here is represented in a slightly different way, not in terms of MT and MW circles, but in terms of S&T parameters, that is a sort of equivalent way of doing. You see again 68% confidence level, 95% confidence level, and here curves that goes in and out when you vary the parameters of the theory to change the masses from scenario 1 to scenario 2 to scenario 3. So for instance, the blue one changes from the mass of the light Higgs from 210 to 235 going out this way. The red one changes from 263 to 360 going according to the error and so on and so forth. But what you have to notice in this plot, that changing a parameter of the theory, so moving along these curves, you always stay in the new model within the circles that are defined by the compatibility with the electroweak data. While with the standard model, you soon get out of it. So another example is the MSSM that we saw before, in which you can do an even better job with new physics coming up at the TeV scale of a completely different kind with this two supersymmetry in order to fit the electroweak data. And we stop here for today. So we have explored the quantum structure of the standard model and how much it can tell us about the scalar sector of the theory and how many indications we have of new physics out of that study. And tomorrow we go into the real phenomenology. We focus on the standard model Higgs again, and we look at the phenomenology of the standard model Higgs as it has been developed to this day, and how it is, and which kind of question we need to ask, and which kind of understanding, theoretical understanding we need to have in order to be able to use and interpret the Tevatron and the LHC data.